A U.S. armored division landed in Normandy with an authorized strength of 232 Sherman tanks. By the end of its campaign in Northwest Europe, its records would show 648 Shermans totally destroyed. That number sounds impossible. A division cannot lose nearly 3 times its starting strength unless the arithmetic is hiding something. It was, because another number was moving in the opposite direction. Roughly 700 more Shermans were knocked out, recovered, repaired, and returned to service. The battlefield saw burning tanks. The maintenance system saw inventory that might still be usable, and that difference changes the way the Sherman has to be judged. The usual comparison begins with armor and gunpowder. In 1944, that comparison could be brutal for an American crew. A standard 75mm Sherman, meeting a Panther across open ground, faced a machine with a much stronger frontal plate and a gun that could kill at ranges where the American weapon might not penetrate from the front. The Panther's glacis was about 80mm thick and sharply sloped. A Sherman crew could maneuver for a side shot, use terrain, call for supporting arms, or avoid the duel. But if the problem was reduced to one tank, one gun, and one frontal engagement, the advantage often belonged to the Panther. American crews understood that without needing a technical table. They learned it through the sight picture. A tank that could be hit before it could answer back did not feel like a good bargain. The Sherman also acquired a reputation for burning after penetration. Some famous nicknames attached to that reputation are still debated by historians in terms of when they appeared and how widely they were actually used. The feeling behind them, however, was real enough. Crews knew that a penetrating hit could turn the fighting compartment into a trap. So when the 3rd Armored Division's Ordnance Liaison Officer, Belton Y. Cooper, later described the wrecks he had to count, he did not write as a man trying to rescue the Sherman's reputation. His memoir was titled Death Traps. That title has shaped the debate ever since. But Cooper's own numbers also point toward a second story. The division did not begin with 648 tanks available to be destroyed. It began with 232 authorized Shermans. Replacements kept arriving. Damaged tanks kept moving backward. Repaired tanks kept moving forward. A vehicle that disappeared from a company in the afternoon could pass through an entirely different military world that most combat histories barely mention. That world was made of recovery crews, mechanics, welders, spare parts, machine tolerances, workshop trucks, hoists, and men who knew how to decide whether a wreck was really a wreck. To understand why that system existed, go back before Normandy, before the Ardennes, before American crews had ever faced Panthers in French fields. When the United States designed the medium tank that became the M4 Sherman, it was designing a machine for a war fought across oceans. The tank had to leave a factory in the United States. It had to fit the American rail system. It had to move through tunnels and over bridges. It had to reach a port, be lifted by dock equipment, fit aboard transport shipping, cross the Atlantic or Pacific, unload on the far side, and then move across military bridges that engineers might have assembled under pressure. Those constraints were not secondary. They were part of the weapon. Weight and width affected shipping. Shipping affected how many vehicles could reach a theater. Bridge capacity affected where the tank could go after it arrived. Every extra ton demanded something from the entire chain behind the tank. That imposed limits. The Sherman entered combat lighter than the Panther, and that helped cap how much armor and gun could be carried. The same design logic that made the tank easier to transport also helped create the tactical disadvantages that crews would later experience in direct confrontations with heavier German armor. That is the uncomfortable part of the story. The logistics advantage was not free. Men paid for some of it at the front, but the design requirement did not stop at transportation. A tank built thousands of miles from the battlefield also had to be repaired thousands of miles from the factory. That meant parts had to be interchangeable. A mechanic in France could not wait for a craftsman to hand-fit every replacement. Components had to arrive in boxes and fit vehicles produced by different plants. Suspension assemblies needed to be removable. Track links needed to be replaceable. Engine access had to allow heavy maintenance without rebuilding the tank around the engine. The Sherman was built in large numbers by multiple factories, yet the maintenance system was expected to treat those machines as members of the same family. That matters because battle damage is rarely tidy. One shell might punch through armor but leave the engine untouched. Another might destroy a road wheel and track without reaching the fighting compartment. A mine might damage the suspension. A mechanical failure might stop a completely undamaged tank. Fire could turn a vehicle into a total loss, but a penetration without a catastrophic burn could leave a surprising amount of expensive machinery intact. A battlefield kill was therefore not automatically a permanent equipment loss. That distinction matters because combat language tends to flatten several different outcomes into one word. A crew might report an enemy tank knocked out because it stopped moving or stopped firing. For the men watching through binoculars, that was enough. The threat had ended for that engagement. But the Ordnance branch had to ask a different set of questions. Did the vehicle burn? Was the hull structurally ruined? Could it be towed? Could intact parts be removed? Could the damage be handled forward? Or did the machine have to move to a deeper shop? Those questions sound administrative. In fact, they determine whether one successful enemy shot removes a tank for hours, days, or forever. The first problem was getting the vehicle back. For that, the Americans fielded purpose-built recovery machines, including the M32 tank recovery vehicle. It used the Sherman chassis with the turret removed and carried recovery equipment, including a heavy winch and an A-frame boom. About WWII 600 were built. That number is easy to skim past. Do not. It means the Army did not treat recovery as an improvisation performed only after a battle went wrong. It manufactured armored vehicles whose job was to retrieve other armored vehicles. Imagine the difference in doctrine that creates. A knocked-out Sherman is sitting forward. The crew has escaped. The tank is damaged, but it has not burned to the ground. The ground is wet. The front may still be close. The question is not simply, is the tank dead? The next question is, can we get it back? If the answer is yes, the tank enters a pipeline. At the lowest level, the crew handles what it can. Battalion mechanics take the next layer of work. More serious repairs move to divisional ordnance units with heavier tools, welding equipment, generators, lifting gear, and stocks of parts. Beyond them are larger Army-level shops and depots for damage that cannot be repaired close to the front. This was organized in maintenance echelons. The exact job changed with the severity of the damage, but the principle remained the same. Move the repair to the level that has the tools to do it. A clean penetration that did not ignite the vehicle could be radically different from a burned-out hull. If the engine and transmission survived, if the turret could still function or be repaired, if the structure remained sound enough, mechanics could cut, weld, replace, patch, and test. A damaged suspension bogie could be swapped as a unit. Track could be rebuilt link by link. An engine could be lifted out instead of condemning the entire machine around it. The source account describes some clean penetrations being turned around in roughly half a day. That was not a promise for every damaged tank. It was an expression of what the system could do when the damage was favorable and the right parts and labor were available. The point is not that Sherman repair was easy. The work could be filthy, dangerous, and repetitive. Recovery crews went toward machines other soldiers had just been forced to leave. Mechanics handled armor pierced by high-velocity rounds, burned wiring, broken track, damaged suspension, and interiors that might still carry the physical evidence of what had happened to the crew. A tank that could not be restored whole could still become a source of usable components for another vehicle. That made standardization more than a factory virtue. It gave the field shop options. A complete suspension bogie could be removed from one hull and installed on another. Track links could be combined. Engines and other assemblies could move through the maintenance chain instead of condemning an entire vehicle because one expensive part had failed. The point is that the Army had deliberately built an organization that expected to attempt recovery and repair at scale. That expectation altered the meaning of a hit. Now compare the recovery problem facing German Panther units. The Panther weighed roughly 45 tons. That weight did not only affect bridges and fuel. It affected what happened after the tank stopped moving. The standard German heavy half-track commonly used for towing, the SDKF-9 FAMO, could not reliably recover a Panther alone. Multiple vehicles might be needed, especially in mud or poor ground. Hooking several unarmored or lightly protected recovery vehicles together near the front created its own vulnerability and traffic problem. Germany understood the need for a better answer and built the Panther, an armored recovery vehicle based on the Panther chassis. It was the right kind of machine. There were simply far fewer of them than the scale of the problem demanded. The source cites production at roughly 350, while German forces were operating thousands of Panthers and Tigers across multiple fronts. Then there was the Panther's mechanical burden. Its final drive became a notorious weakness. The assembly had to transmit power to the drive sprockets of a heavy vehicle. The source describes a double-spur gear design that was under severe load and reports failures at very low mileage in some vehicles. A Panther could therefore become immobile without being hit at all, and an immobile heavy tank created the same recovery question as a battle-damaged one. Can it be moved before the front moves? If the answer was no, the tank's tactical quality stopped mattering. A vehicle with excellent armor and a powerful gun has no combat value after its crew is forced to abandon it. This became especially important during retreats. When an army is advancing, recovery can happen behind a front that is moving away from the wreck. When an army is retreating, the geometry reverses. Workshops have to move. TOW vehicles are scarce. Fuel is scarce. Roads are crowded. A tank that breaks down may have hours, not days, before the enemy reaches it. In the retreat from Normandy toward the Seine in August 1944, German armored formations lost vehicles not only to Allied fire but also to breakdown, fuel shortage, and the inability to recover heavy equipment while the front was collapsing backward. This is where the tank versus tank comparison begins to fail. A tank can be superior in protection and firepower while belonging to a weaker recovery environment. Those truths do not cancel each other. They operate at different levels. German designers could produce a vehicle with formidable frontal protection, yet the field army still had to provide fuel, spare parts, trained mechanics, towing capacity, workshop space, and enough time to perform the repair. Every increase in vehicle weight raised the burden on that support structure. The same logic worked in the other direction for the Sherman. Its tactical compromises did not become virtues merely because it was easier to move and maintain. A crew facing a Panther did not receive extra protection from the knowledge that a replacement engine existed somewhere behind the front, but an army commander planning the next day's advance cared deeply about how many disabled tanks could be made serviceable before that advance began. A tactical chart asks what one Panther can do to one Sherman. A campaign asks a different question. How many useful tanks can each side place in the line tomorrow morning? Those are not the same problem. The Panther's armor and gun could produce a battlefield advantage. The Sherman system could reduce the permanence of some battlefield losses. Production was part of that. The United States built roughly 49,000 Shermans, compared with about 6,000 Panthers. But production alone does not explain what happened at the front. If every disabled Sherman had been abandoned, American factories would still have faced a much larger replacement burden. Recovery and repair multiplied the value of production by returning machines the factories did not have to replace immediately. A repaired tank was not a new tank. It was capacity recovered from a machine the enemy had already spent ammunition and effort to stop. There was another reason many Shermans could be recovered. The crew often survived the hit. British operational research in Northwest Europe studied knocked-out tanks and tried to measure the human cost. The source summarizes the result as roughly 1 fatality per knocked-out Sherman on average, meaning most of a 5-man crew survived the loss of the vehicle. That mattered twice. First, surviving crewmen could escape a damaged tank and live. Second, the Army did not have to replace 5 trained men every time it replaced or repaired one machine. The Sherman also evolved during the war in response to what investigators learned about fires. The popular explanation focused on gasoline. Wartime investigation instead pointed strongly toward ammunition as a major cause of catastrophic burning after penetration. Rounds stored in vulnerable positions could ignite when struck. The response was an engineering change known as wet ammunition stowage. Ammunition was moved lower and protected in liquid-filled jackets. The source cites a major reduction in the proportion of penetrated Shermans that burned, from very high early war figures to a much smaller fraction in vehicles with the improved system. The exact percentages in historical discussions vary with sample, definition, and vehicle type. The important point is the direction of the change. The Army identified a mechanism of loss and redesigned around it while production continued. That is the same logic that appears everywhere else in the Sherman story. Transportability was not glamorous, but it put tanks across oceans. Interchangeability was not glamorous, but it let mechanics use standardized parts far from the factories. Recovery vehicles were not glamorous, but they turned abandoned wrecks into repair candidates. Maintenance echelons were not glamorous, but they gave each kind of damage somewhere to go. Crew escape was not glamorous, but it preserved trained men. Wet stowage was not glamorous, but it attacked one specific mechanism that made penetrations more deadly. None of those features makes a 75mm Sherman stronger than a Panther's frontal plate. That is why two apparently contradictory judgments can both be true. At the level of a direct engagement, the Sherman could be badly outmatched by heavier German armor. At the level of an army trying to sustain an offensive across a continent, the Sherman belonged to a system that was exceptionally difficult to exhaust. The difference was visible in the work behind the lines. A tank recovery crew did not ask whether a vehicle had won its duel. It looked at tracks, suspension, hull damage, fire damage, engine condition, and location. A mechanic did not care whether a shell had produced a dramatic kill. He cared whether the transmission still turned, whether the turret ring was usable, whether a replacement bogie was available, whether the hole could be patched, and whether the machine could be tested and sent forward. A supply system did not see one heroic tank. It saw flows of parts, vehicles, fuel, replacement crews, tow capacity, and time. That is why battlefield loss statistics can mislead when they are read without recovery statistics. Knocked out is an event. Destroyed is a condition. Abandoned is a logistical outcome. Return to service is a different outcome again. A campaign is shaped by all four. Belton Cooper spent the war close enough to the damage to remember the wrecks decades later. His account is one reason the Sherman still carries the label Death Trap in popular memory. But the same account, read as an ordnance story instead of only a tanker story, reveals something else. The American advantage was not that its tanks could not be killed. They could. It was not that armor quality did not matter. It did. And it was not simply that the United States could build replacements faster than Germany. That mattered too. The deeper advantage was that the Army tried to keep a battlefield hit from automatically becoming a permanent subtraction. A damaged machine could be dragged backward. A damaged component could be replaced. A penetration could be patched if the structure survived. A crew that escaped could return to another tank. A design flaw that showed up in combat could be attacked with a production change. The Sherman was part of a loop. Build, ship, fight, recover, repair, return. The loop did not make the tank invulnerable. It made the force more recoverable. And in a campaign of hundreds of miles, that distinction mattered more every morning the advance continued. The decisive question was not whether a tank had been hit. It was whether the Army could turn that hit into a temporary absence instead of a permanent loss.